Chapter 7 is all about linear association, beginning with correlation tests. So the data, pretty much throughout the chapter, are pairs. So we have x1, y1 up to xn, yn. And for now, we want to know if there is a linear association between them. So the linear part we'll talk more about a little bit later. By association, I mean that if x is large, y is large. If x is small, y is small. So that's a positive association. A negative association would be if x is large, y is small, and if y is large, x is small. Okay, so let's just start by taking a look at an example. I've got some data here in R that you'll also find in the book that has the times it took a member of a fraternity to run 100 yards, so that's X, and then they chugged a beer, and then they ran 100 yards again, that's Y, and both of them are times in seconds. And then I can do a scatter plot, which I will need to reveal for you. So there's the scatter plot. And I want to know if there's an association between the times it takes these members of the fraternity to run 100 yards before and after a beer. To my eye, there is kind of an increasing relationship between the X's, time before a beer, and the Y's, time after a beer. But I want a measure of that, and I want to be able to test if that measure reveals a substantial, a statistically significant relationship. So now I'm going to try to remind you of some definitions that I think you would have encountered before, and we'll see how those can be used in a test. Okay, so we're going to talk now about measures of association. The first one is covariance. So the covariance of random variables y and x is an expectation of the product between differences between the variables and their means. Okay, so that's a kind of technical definition. It extends variance because the covariance between a random variable and itself is the variance of that random variable. And the same thing if we do covariance of x and x, we get variance of x. That's kind of a theoretical construct. When we have data, we'll be interested in estimating the covariance, and there are many ways to do that, but one of them is simply to extend the definition of the estimate of variance, which we usually call S or S squared, and extend that to covariance. So we could do that in the following way. I'm going to define what I call SXY, and it's going to be an average of a sum of discrepancies between the y variables and the estimate of their average, and the x variables and the estimate of its average. So this is the analog of variance, or the estimate of variance, to covariance, basically following the formula describing the theoretical estimate of covariance, or theoretical definition of covariance. And again, you'll notice that SYY, or we could call that SY squared, is the same as our estimate S squared for estimating variance. So if I pop over to R, I can do some of these calculations. right? So first of all, let's extract how many observations we have, and I could get that from the length of x too, because they're the same length. And I've got y bar is the mean of y, and x bar is the mean of x. And then I could sum up y minus y bar times x minus x bar and divide that by n minus 1. And that would be my estimate of covariance. Or more simply, in R, I can do cov of y and x, or x and y, because there's symmetry in the use of x and y in the formula. So I could call that x, s, y, x, just to save it to use for later. Okay. The problem with using cov as a measure of association is that it has both scale, that means variance, and association at the same time. So it's hard to know when you see a number like 2.9 whether that's a big number or a small number, because it's telling you something simultaneously about the scale of x's and y's and about the association through the product of discrepancies between the observations and their average. So what people do instead is they look at something called correlation. And be very careful here. Cov can look a lot like core, because R and V, depending on how good your handwriting is, and mine isn't terrific, a V and an R could look kind of similar. So be careful. I'm defining correlation now, and correlation is covariance divided by variance, or the square root of the variance of y and x. So it's normalizing covariance by the scales of y and x, giving you a measure that's always a ratio. So it's going to be between -1 and 1. Okay, and this gets called rho, or you could write rho yx. Whoops, that's not yx. There we go, yx. So that's the theoretical definition of covariance. If rho is equal to 0, then there is no linear, again, we'll talk more about why I'm saying linear, association between y and x. And if we want to estimate this quantity, we can just take our estimate of covariance and divide by estimates of standard deviation. And we can call that r, y, x, or just simply r if it's obvious which variables are involved. So again, back over in R, I can calculate variances. So sy squared is variance of y, and sx squared is variance of x. And I can then do syx divided by the square root of sy squared times sx squared. And that will give me the correlation. Or I can just do correlation between y and x as kind of a shorthand. And I can save that as r so we can use it later. Okay, so that's correlation. Now, since we know that rho equals 0 corresponds to no association, this gives us a framework for testing. Okay, so for now we're going to focus on testing. You can also calculate confidence intervals, but I'm going to skip that. You can find that in the book. And I'm also always going to focus on, in this video anyway, testing the null hypothesis that correlation is 0 versus the alternative that it's not. You can test rho equals some other value, rho not, but I'm not doing that in this video. See the book for extensions of what I'm going to show you here to the more general setup. What I'm showing you here, testing for rho equals 0, that is testing for some or no association, is the most common case. So I'm not really jipping you. I'm showing you about 90% of correlation, but as always, these videos aren't complete. I'm trying to keep them short, so please have a look in the book for the more general setup. Okay, and we're gonna have to pick, so I've got the hypotheses, right? I need models, so I'm gonna use independent Gaussian models for y and x. So y1 up to yn is IID Gaussian with a mean of mu y, and a variance of sigma y squared, and x, similarly, so this is like a chapter 5 setup, and they're also independent between samples because the null hypothesis says that the correlation is 0. So this tells us how to simulate, but we need estimates of the variance parameters. So let me remind you from chapter 5, we have that sigma y squareds can be obtained following chi-squared distributions using estimates of variance, and sigma x's similarly. So this tells us how we simulate, and in fact I can borrow the exact code from from chapter 5 in order to do that, but I'm going to type it fresh here. So simulate using chapter 5 under the null hypothesis that there's no association. I'm going to write rho out here. I know rho looks kind of like a P when you draw it, but I don't want to use P because that's going to be confusing. So I'll just write out rho in English. Okay, I need a big simulation. I need to draw from the chi-squared distribution. So sigma 2y is going to be n minus 1 times s y2 divided by r chi-squared. I need one sample with degrees of freedom n minus 1. And then I need the same thing for the x's. Well, maybe let's do the draws first of the y's. So given that, I can do r norm n. It doesn't matter what you use for the mean, so I'm just going to put y bar in, but you can put something else. That's totally fine. And then square root of sigma 2y. Got to spell sigma correct. And then I can cut and paste all of this for the x's and replace some y's with, whoops, with x's. Oops, I can see I typed y bar wrong, and sigma 2x. Okay, so now I've got my samples of x's and y's, and then I can save the correlation between them. So I'm virtualizing this modeling setup, but instead of, in chapter 5, we looked at differences in means, but we don't really care about means now. And in chapter 6, we looked at differences in variance, or ratios of variances, but we don't care about variance now. What we care about is correlation. So I need to make some space to save those correlations and then save them. And hopefully I didn't make any mistakes and this will run. So there it goes, it's done, and I can visualize the samples. So usual thing, histogram of all of these virtual statistics, and I have to reveal the plot for you so you can see it. There it is. So these are the estimates of correlation that you get from populations that are Gaussian of size n with estimated variances. So you can get correlations that they're usually around 0, but sometimes you see some really high or really low correlations just due to random chance. And statistics is all about assessing that random chance possibility when you're looking at an estimate that you took from data. So our estimate from data is this value r that we calculated from data. And, oops, I got to tell them r, I need a vertical line. And here, when I look at the estimate from data and I compare it visually to the null distribution that I get from sampling from a model under the null hypothesis of no correlation, totally separate x and y samples, I see what I judge to be a rare occurrence. The observed value is rare under the null distribution. But I can be quantitative about that with a p-value calculated in the usual way. A two-sided p-value could be calculated like that. Oh, I don't know why I wrote 2. I meant to write r. There we go. So it looks like it's a 1 in 100 probability, which is less than 1 in 20. So reject the null hypothesis of rho equals 0. So just like chapter 5, but different statistic, but the same kind of visual and p-value calculation as we ever have in this setup. Okay, back to the notes here. That was by simulation. The math on this is hard. In fact, this is going to be the first time that I'm going to totally skip showing you the work and going right to the result, because it's beyond the scope of an undergrad or introductory grad class. So I'm just going to tell you it can be shown that under the null hypothesis of 0 correlation, if you take r, which is, so r is the covariance between y and x is a shorthand, so that's what I mean by r. This covariance, if you multiply it by the square root of n minus 2 and divide by the square root of 1 minus the covariance squared, that has a t distribution with n minus 2 degrees of freedom. And people call this, I'll just erase this because I just want to be clear. People call this u. And when you use it in the calculation, you replace the big R with the little r that you estimated from data in order to calculate the p-value. So I'll show you exactly what I mean by that. So right. So u is equal to r times square root of n minus 2 divided by square root of 1 minus r squared. So that value u is positive, so I can do 2 times pt u n minus 2 degrees of freedom, lower tail equals false. Okay, so I get 0.0078, so if I round to the nearest 100th place, I get 0.001, the same way I get 0.001 here. So that is the math way. But I didn't give you how the math works, but it's reassuring. You can see that I'm getting close results with my simulation, and they should agree in more detail with a larger sample size. Okay. Oh, I see a mistake. I'm like wondering why this isn't all the same. I see a mistake here. This should be a 2. Let's redo that. Oh, there we go. Much closer agreement. So our simulation gives a even closer result when I type the formula correctly. That's what you get for doing this live. All right.